Okay, this is Mr. Mumford from his shed. Doing a lesson on the second part of stationary waves lesson, and a beautiful sunny day. And I showed you a lesson before showing you how stationary waves were formed, and I left you with these little questions here, which I hope you should have answered. And it says, first question, what are the points of no displacement called? And that's going to be the point just here, here, and here, and they are called nodes. What are the points of maximum displacement called? And those are this point here and over here, and they're called antinodes. Then says, in terms of wavelength, what is the distance between adjacent nodes? So if I've got a node here and a node there, get my little pen. There's a node here, and there's a node just there. The distance between those is going to be lambda. The reason why is, go away, you horrible thing, is going all the way through there. It's going to be one full wavelength. Therefore, that's going to be half wavelength between this node here and that node just there. And then it says in terms of wavelength, what is distance between adjacent antinodes? So if I got an antinode here, got an antinode there, I think you can see now exactly the same as the last one. Adjacent nodes, it's still going to be lambda over 2. And then it says, in the region between successive nodes, comment on the phase and amplitude of the particles. Well, if I take this node here and that node just there, these particles are well, it changes with time. Sometimes we dot that, showing the fact it goes up here, down there. These particles vibrating down, they all have different amplitudes. Okay, where you've got a maximum amplitude of the particle vibrating there, to a small amplitude over here. So they all have different amplitude, but you should see the fact they go up and down in phase. This goes up and down at the same time, this goes up and down, or the particles go along here. So to answer that question is, in the region between successive nodes, the particles all have the same phase, but they have a different amplitude. And then comment on the phase relationship between adjacent loops. So what I mean by that, went the wrong way, is I've got a loop here and I've got a loop here. So basically, if you're looking at the particle here, this particle is about, I'm going to change my to a different color pen now. Red, yeah. That's about to go down if I go forward in time, and that is about to go up. Therefore, can you see they're going to have 180 degrees, or they're going to be pi out of phase? And that's looking at that particle there compared to this particle here. So therefore, the answer to that one is, between adjacent loops, the particles are going to be pi out of phase. Cool. Now, this is a very strange little bit, but the examinations do ask you about this, is compare stationary and progressive waves. You've got a little section in your book, okay? And it's all on page 183, but I thought I'd better explain it to you. And it's looking at stationary waves and also looking at progressive waves, okay? So if you first of all got your stationary wave, and it says about the frequency, so I can put stationary here, okay? With the frequency here, all the particles are going to vibrate, okay, at the same frequency. And it does mention in your book about nodes, because the nodes, there's no vibration whatsoever, but they go up and down at the same frequency. I mean, all the, oh gosh, going back over here, these go up and down at the same frequency in your stationary wave. But when you look at the big progressive wave, it's exactly the same thing again. All the waves go up and down again at exactly the same frequency. But when you look at amplitude, okay, for your stationary waves going down here, that have then a different amplitude. Now remember, going back to the slide over here, where you have here, the particles here have a very small amplitude, big amplitude, and small amplitudes. They all have different amplitudes. But when you go to a progressive wave, this wave is traveling along with time going this way here. This particle will vibrate up and down, but they all are vibrating up and down at a different time going through that. Measure the particles vibrating up and down. Eventually this particle will vibrate down to maximum amplitude, but so will this one as well, because a wave is traveling along. So the amplitude of all these particles will be the same, and that's for a progressive wave. Now the phase difference between particles, okay, and this, yeah, it does a bit weird in the book. It talks about here going across. It really depends how you look at it, okay. And what they do is in your book they say I'll probably a little bit rubbing out actually here. Tidy this up a little bit. Is they talk about in a stationary wave. They say then that they have something called, get back to my pen, M, is it M lambda? I think, sorry, M pi it calls it, apologies. Now, this basis do, M is going to be a number of nodes, so you can have a node here, and a node here, and a node there. Now, what this talking about here is going to talk about the phase difference, it's going to be 180 degrees from here to there. So, literally, from this loop going to that loop, they're going to have a pi phase difference. What it means by then, m lambda, if I go across this loop over here, which is the next loop, if I compare this loop here to that loop there, then it's going to be 2 pi. What I mean by that is that one here and that one there are going up and down at the same time. Therefore, 2 pi is they're going to be in phase, or we can say it's 360 degrees. I wouldn't worry too much about that, but m lambda, sorry, m pi, it's basically looking at consecutive nodes there. Okay, and then get back to my question, is then looking at the phase difference between the particles. Well, this one here is, we talked about before, as a wave going along. When we talk about the fact that that one is going to be 0 going through one complete cycle, and that's going to be pi going over here. And they bring out this formula, we got 2 pi d over lambda. That's because basically, apologies, that's meant to be 2 pi. That's going to be 2 pi going through over here, and that's going to be your pi. They can all have a slightly different phase going through all the way here. Okay, I don't use that formula, as I know from going from that part of the way to that part of the way is going to be pi, and over there is going to be 2 pi, and going to over that point there is going to be pi over 4. Okay, see different parts to it. So that answers that little questions. That answers all the questions I had going over here. Right, I'm going to end this video now, and then I'm going to upload a next video looking at then waves on strings and looking at fundamental frequencies. Over and out.